Sarnia, Ontario, January 1942. A chemical engineer named Ralph Rowzee stares at an impossible deadline scrawled across blueprints spread over his desk. Build a massive industrial plant, perfect a chemical process that barely exists outside laboratory conditions. Start producing synthetic rubber within 18 months. Oh, and one more thing. Do what would normally require 12 years of development, or watch the Allied war effort collapse. No pressure. Here's what makes this story remarkable. When Rowzee accepted this assignment, Canada possessed exactly zero synthetic rubber production capacity. None. The country that would soon supply rubber for hundreds of thousands of military vehicles couldn't make a single tire without natural rubber from trees. And in February 1942, every single one of those trees fell into Japanese hands. What happened next didn't just save Canada's war production, it changed industrial history. Let's establish what was at stake. Rubber wasn't just another wartime commodity. Each Sherman tank required 1 full ton of rubber. A single battleship, 70 to 5 tons. Multiply that across thousands of military vehicles, aircraft, ships, and essential equipment. Gas masks, electrical insulation, inflatable rafts, shock absorbers, piping, gaskets, and you begin to grasp the magnitude of the crisis. Before Pearl Harbor, 97% of the world's natural rubber came from Southeast Asian plantations. Britain controlled Malaya and Singapore. The Dutch governed the East Indies. France held Indochina. These territories produced nearly all the latex that kept Allied industries running. Then came December 8, 1941. Japanese forces swept through Southeast Asia like a tsunami. Within weeks, they controlled virtually every rubber plantation that mattered. By February 15, 1942, when Lieutenant General Arthur Percival surrendered Singapore to General Tomoyuki Yamashita, the catastrophe was complete. The United States lost access to 90% of its rubber supply overnight. Britain and Canada faced the same devastating reality. An American report to Congress spelled out the consequences with chilling clarity. Of all critical and strategic materials, rubber presents the greatest threat to the safety of our nation and the success of the Allied cause. If we fail to secure quickly a large new rubber supply, our war effort and our domestic economy will both collapse. Not might collapse, will collapse. Canada's predicament was particularly acute. The nation was ramping up unprecedented military production. Over 800,000 military vehicles would eventually roll out of Canadian factories during the war. But without rubber, those assembly lines would grind to a halt. Trucks couldn't move, planes couldn't fly, ships couldn't sail. The entire war machine would seize up like Someone needed to solve this problem fast. That someone turned out to be a powerful Canadian cabinet minister named Clarence Decatur Howe, a man who didn't believe in the word impossible. To understand how Canada pulled off this industrial miracle, you need to know about C.D. Howe. Born in Waltham, Massachusetts in 1886, Howe trained as a civil engineer at MIT. He moved to Canada in 1908, drawn north by opportunities in grain elevator construction. Throughout the 1910s and 1920s, he built a reputation for completing massive infrastructure projects on time and under budget. When others saw obstacles, Howe saw solutions waiting to be engineered. By 1935, he'd entered politics, winning a seat in Prime Minister Mackenzie King's Liberal government. King appointed him Minister of Transport, then Minister of Munitions and Supply when war erupted in 1939. This second title gave Howe extraordinary powers. He could incorporate companies, seize facilities, redirect resources, and bend Canadian industry to meet wartime needs. Howe wielded these powers with ruthless efficiency. Colleagues called him the Minister of Everything. He didn't wait for committees or consensus. When the nation needed something built, Howe authorized it and expected results. So when the rubber crisis materialized in early 1942, Howe acted with characteristic decisiveness. First, he needed expertise. Enter Ralph Rowzee, a 34-year-old chemical engineer who worked for Goodyear Tire and Rubber Company in Akron, Ohio. Rowzee was among perhaps 24 people in North America who truly understood synthetic rubber production. He'd been experimenting with polymer chemistry since the early 1930s, back when synthetic rubber was considered an inferior substitute for natural latex. Howe recruited Rowzee personally. The pitch was straightforward. Leave your comfortable corporate position and lead the most ambitious chemical engineering project in Canadian history. Work 16-hour days. Accept an impossible timeline. potentially fail spectacularly in front of the entire Allied High Command? Rowzee said yes. Now came the technological challenge. How do you make rubber without rubber trees? The answer lay in chemistry rather than botany. Natural rubber is a polymer, long chains of molecules called isoprene units. Synthetic rubber mimics this structure using petroleum-based chemicals. German chemists at IG Farben had cracked this puzzle in the 1930s, developing a synthetic rubber called Buna S. The Buna came from butadiene and sodium, natrium in Latin. The S stood for styrene. Buna S combined two chemical building blocks, butadiene and styrene, mixed in a ratio of 3 parts to 1. When polymerized together through a process called emulsion polymerization, these chemicals formed synthetic rubber, with properties remarkably similar to natural rubber. Here's where it gets interesting. You could manufacture butadiene from petroleum through catalytic cracking, but there was another route, one that would prove crucial for Canada. You could also produce butadiene from ethanol, regular grain alcohol, the stuff distilled from corn, wheat, and other agricultural products. Soviet chemist Sergei Lebedev had developed this process in 1928, converting ethanol into butadiene through a 2-step catalytic process. First, ethanol was dehydrogenated into acetaldehyde. Then, this acetaldehyde reacted with additional ethanol over a catalyst to produce butadiene. The Soviets built their entire synthetic rubber industry on this foundation during the 1930s. Canada, with its vast grain-producing prairies, could potentially do the same. But knowing the chemistry and actually building a production facility were entirely different challenges. The scale required was staggering. To supply Canada's needs and contribute to broader Allied production, the proposed plant would need to produce thousands of tons of synthetic rubber monthly. No such facility existed in Canada. The necessary chemical engineering expertise barely existed in North America, outside a handful of corporate laboratories and university research departments. Howe's solution was characteristically bold. Build everything at once. Don't wait for pilot plants or phased development. Design the full-scale production facility immediately and start construction while simultaneously perfecting the chemistry. He selected Sarnia, Ontario as the location. The choice made perfect sense. Sarnia sat on the St. Clair River at the southern tip of Lake Huron, providing excellent water access for transportation and industrial cooling. More importantly, Sarnia was already home to Imperial Oil's largest refinery, plus chemical plants operated by Canadian Industries Limited. The infrastructure and skilled workforce already existed. In January 1942, Howe authorized creation of Polymer Corporation, a crown corporation wholly owned by the Canadian government. He appointed John Robert Nicholson, his deputy controller of supplies, as the company's first general manager. Nicholson would handle administration. Rowzee would run the technical side. Together they faced a task that seemed to violate the laws of physics and economics. Industry estimates suggested developing and building a synthetic rubber plant normally required 10 to 12 years. Pilot plants had to be constructed and tested. Chemical processes needed optimization. Equipment had to be designed, fabricated, and debugged. Workers required training in entirely new industrial processes. Rowzee's team had 18 months of industrial processes, and that timeline wasn't negotiable. Every month of delay meant thousands more military vehicles sitting idle, waiting for rubber tires that didn't exist. It meant Allied soldiers lacking gas masks, electrical wire going uninsulated, ships delayed in port. The clock was ticking. By March 1942, even as Japanese forces consolidated control over Southeast Asia's rubber plantations, bulldozers were breaking ground in Sarnia. Construction crews worked around the clock. Rowzee assembled a technical team drawing from universities, oil companies, chemical firms. Anyone with relevant expertise got recruited, regardless of nationality. The Canadian government essentially wrote a blank check. Cost overruns? Approved. Need specialized equipment from the United States? Purchased. Require rare catalysts or experimental materials? Procured through whatever channels necessary. But money alone couldn't solve the fundamental problem. Nobody had ever built a synthetic rubber plant on this scale using grain alcohol as the feedstock. What happened over the next 18 months would determine whether Canada remained a vital contributor to Allied victory or became a sidelined nation unable to equip its own military, let alone help supply Britain, the Soviet Union, and other partners. The fate of hundreds of thousands of soldiers, sailors, and airmen hinged on whether Ralph Rowzee could turn grain into rubber fast enough. Spring 1942 brought no relief from the rubber crisis. If anything, the situation deteriorated. American civilian tire production ceased entirely in January. By April, the United States instituted rubber rationing. Citizens could purchase new tires only with government-issued coupons, and those coupons were nearly impossible to obtain. A massive scrap rubber collection drive mobilized children and civic organizations to gather old tires, rubber mats, garden hoses. Anything containing rubber got recycled. These desperate measures bought time, nothing more. The existing stockpile wouldn't last through 1943. Meanwhile, in Sarnia, Rowzee confronted challenges multiplying faster than solutions emerged. The first major obstacle was sourcing raw materials. Producing synthetic rubber required not just ethanol, but also styrene, the second crucial component. Styrene came from petroleum refining, specifically from processes that extracted aromatic hydrocarbons from crude oil. The problem? North American styrene production was minimal. The few existing plants primarily supplied styrene for making polystyrene plastics, not rubber. Howe moved quickly. He approached Dow Chemical, which operated facilities in nearby Sarnia, and essentially ordered them to build a massive styrene plant adjacent to the Polymer site. Dow initially balked at the compressed timeline. Howe made it clear this wasn't a negotiation. By summer 1942, Dow began constructing what would become one of North America's largest styrene production facilities. This solved one problem while creating another: coordination. Two massive chemical plants, Dow's styrene facility and Polymer's rubber production complex, had to be designed, built, and brought online in perfect synchronization. If styrene production started too early, Dow would be making material with no buyer and nowhere to store it. If Polymer came online first, they'd have reactors sitting idle waiting for raw materials. Rowzee essentially had to orchestrate an industrial ballet while the music was still being composed. The technical challenges multiplied daily. Converting ethanol to butadiene required specialized catalysts, materials that accelerate chemical reactions without being consumed. The catalyst Rowzee's team selected was based on tantalum and zinc oxide, supported on activated silica. Manufacturing these catalysts at industrial scale proved maddeningly difficult. Small batches worked beautifully in laboratory conditions. Scale up to factory production, and efficiency plummeted. Weeks were lost troubleshooting catalyst formulations. Temperature control became critical, run the reactor too hot, and unwanted byproducts formed. Too cool, and conversion efficiency dropped below economic viability. Finding the sweet spot required countless experimental runs, each consuming time they didn't have. Then there was the reactor design itself. The ethanol to butadiene conversion generated substantial heat. Industrial reactors needed sophisticated cooling systems to maintain optimal temperatures. But wartime material shortages meant stainless steel and specialized alloys were nearly impossible to obtain. Rowzee's engineers improvised alternatives, often working with equipment designed for entirely different processes and adapting it on the fly. Procurement became a daily battle. Every piece of equipment, every valve, every meter required import licenses, transportation approval, installation permits. Normal bureaucratic processes that might take months got compressed into days through Howe's intervention. He personally intervened whenever supply bottlenecks threatened the timeline, cutting through red tape with ministerial authority. The workforce posed its own challenges. Chemical engineering was still a relatively young profession in 1942. Universities produced perhaps a few hundred graduates annually across all of North America. Polymer needed dozens of these specialized engineers immediately, plus hundreds of skilled technicians, operators, and support personnel. Rowzee recruited aggressively. He poached talent from American rubber companies, offering enhanced salaries and appealing to patriotic duty. He brought in university professors as consultants, essentially deputizing academia into wartime service. Fresh graduates got hired before completing their degrees, learning on the job in what amounted to the world's largest chemical engineering apprenticeship program. By summer 1942, the Sarnia site resembled organized chaos. Multiple buildings rose simultaneously: the butadiene production units, polymerization facilities, storage tanks, utilities infrastructure, control rooms, laboratories. Construction crews worked 3 shifts daily. Welders, electricians, pipe fitters, concrete workers. Everyone raced against a deadline that grew more daunting each month. and hanging over everything was the knowledge that Allied forces were losing ground in multiple theaters. German U-boats were sinking merchant ships faster than replacements could be built. Japanese forces controlled vast Pacific territories. The Soviet Union was bleeding under sustained German assault. North Africa remained contested. Everywhere the outcome hinged on logistics, moving supplies where they were needed. And logistics meant trucks, tires, and rubber. No pressure at all. By September 1942, the plant structure was largely complete. Now came the truly terrifying part. Startup. Would the chemistry actually work at industrial scale? Would the equipment function as designed? Could operators trained in mere weeks safely run processes that were still being refined? Rowzee prepared for the first test runs knowing that failure could doom the entire project. If the chemistry didn't work, if yields were too low, if product quality was inadequate, Canada would have spent millions on a white elephant while the rubber shortage strangled Allied production. Everything rode on what happened next. October 1942. The moment arrived. Rowzee stood in the control room as operators prepared to feed ethanol into the first reactor. Months of planning, millions of dollars, and thousands of person-hours came down to whether this chemical cascade would produce butadiene or just produce an expensive mess. Temperature gauges climbed toward operating range. Pressure stabilized. Catalyst beds were activated and ready. Ethanol began flowing through the system. For the first hour, nothing seemed wrong, but nothing seemed conclusively right either. Chemical processes at this scale don't provide instant feedback. Material had to flow through multiple stages: conversion, separation, purification. Samples required laboratory analysis. Everyone waited. Then, finally, results. Butadiene was emerging from the process train. Not in theoretical quantities calculated on paper, but actual, measurable butadiene gas flowing into collection tanks. The relief was audible. Rowzee's team had cleared the first hurdle, but butadiene was only half the equation. Next came polymerization, combining butadiene with styrene from Dow's adjacent plant to create actual synthetic rubber. This process used emulsion polymerization, a technique developed in Germany and refined in American laboratories. The principle resembled making mayonnaise. You created a stable emulsion of tiny droplets suspended in water with soap acting as an emulsifier. Inside these droplets, butadiene and styrene molecules linked together into long polymer chains. Temperature control was absolutely critical. Too hot, and you got poorly structured polymers with terrible mechanical properties. Too cool, and the reaction proceeded so slowly that economic production became impossible. The target temperature range was surprisingly narrow, around 50 degrees Celsius, maintained with precision. The first polymerization batch ran in November 1942. Scientists and engineers crowded around as the reaction mixture churned in massive reactors. Hours passed. Sample analysis began. The results showed promise, but the material wasn't quite right. The molecular weight distribution was off. Mechanical testing revealed the rubber was too soft, lacking the tensile strength needed for demanding applications like tire production. This wasn't failure. It was the beginning of optimization. Over the following weeks, Rowzee's team adjusted dozens of variables. Catalyst concentrations changed. Reaction times were tweaked. Temperature profiles were refined. The soap formulation was modified. Each adjustment produced slightly better results. The rubber became firmer, more resilient. Tensile strength improved. Abrasion resistance, crucial for tires, gradually approached acceptable levels. By December 1942, Polymer Corporation was producing synthetic rubber, not in the quantities needed, not yet with consistent quality, but the fundamental process worked. The chemistry was sound. Then came winter, and Canadian winter presented challenges German laboratories had never encountered. Pipes froze. Outdoor equipment contracted in the cold, throwing calibrations off. Workers battled blizzards. Material handling became treacherous when everything was coated in ice. The plant's design hadn't fully accounted for operating in temperatures that routinely dropped below -20 Celsius. Hasty modifications were implemented, adding insulation, installing heating systems, designing cold weather procedures. Through it all, production continued. Some days, output was minimal. Other days, yields approached target levels. Slowly, painfully, the operation stabilized. Spring 1943 brought validation. In March, the first commercial quality synthetic rubber left Polymer's production lines. The material was designated GR Government rubber styrene, using the same nomenclature adopted by the United States for its synthetic rubber program. Samples went to tire manufacturers. Engineers subjected the material to brutal stress tests. The US military, Canadian Armed Forces, and British procurement officers all evaluated Polymer's rubber. Reports came back positive. The stuff worked. Not identically to natural rubber, synthetic rubber had different properties, requiring adjusted formulations for specific applications, but it worked. You could make tires from it. You could insulate electrical systems. You could manufacture gaskets, hoses, and countless other essential components. Production ramped up through spring and summer 1943. By August, Polymer was outputting 3,300 tons of synthetic rubber monthly. By year's end, annual production exceeded 40,000 tons. Those numbers represented more than industrial output. Each ton of synthetic rubber translated directly into military capability, into trucks that could move supplies to the front lines, into aircraft, into ships that could transport troops across oceans. The rubber shortage, while not completely solved, had been broken. Allied production was no longer constrained by access to Southeast Asian plantations. Synthetic rubber filled the gap. And Canada, a nation that 18 months earlier possessed zero synthetic rubber production capability, was now producing enough rubber to supply its entire military and contribute substantially to British and American needs. Rowzee's impossible deadline hadn't just been met, it had been beaten. Success created new challenges. Once Polymer proved the chemistry worked and the facility could produce rubber at scale, demand exploded. Military planners revised their requirements upward. If Canada could make 40,000 tons annually, could they make 60,000? What about 80,000? The Canadian government faced a decision: maintain current production or expand aggressively. Howe characteristically chose expansion. Throughout 1944, Polymer underwent continuous modification. Additional reactor capacity was added. Storage facilities expanded. The workforce grew to over 1,000 employees. The second polymerization train came online, nearly doubling output. This expansion happened while maintaining existing production, essentially renovating a factory while it operated at full capacity. Maintenance windows were measured in hours, not days. Shutdowns for upgrades had to be meticulously planned to minimize production losses. The technical complexity was staggering. Synthetic rubber production involved managing dozens of simultaneous chemical processes, each with critical parameters requiring constant monitoring. A single mistake, wrong temperature, incorrect catalyst ratio, contaminated feedstock could ruin entire batches worth thousands of dollars. Quality control became its own discipline. Polymer established extensive testing laboratories staffed by chemists who analyzed samples from every production batch. Molecular weight distribution, tensile strength, elongation characteristics, tear resistance, hardness, each parameter was measured and recorded. Customer feedback loops were established with tire manufacturers. When rubber batches performed poorly in specific applications, engineers traced the problem back through production records, identifying which process variations caused the issues. This data-driven approach was revolutionary for its time. Most industrial processes in the 1940s relied heavily on operator experience and intuition. Polymer Corporation applied rigorous statistical analysis and continuous process improvement, techniques that wouldn't become standard industrial practice for decades. The ethanol supply chain also required constant attention, producing 47 miles, plus tons of synthetic rubber annually consumed enormous quantities of grain alcohol. Polymer had to coordinate with distilleries across Canada, ensuring reliable supply of consistent quality ethanol. This created an unusual agricultural connection to military production. Farmers growing corn and wheat in Saskatchewan and Manitoba were, in effect, supplying raw material for truck tires used in North African deserts and European battlefields. The industrial chain from prairie field to military depot spanned thousands of miles and dozens of processing steps. Styrene supply from Dow Chemical also scaled up. The two plants became intimately linked. Dow's production schedules dictated Polymer's operating rates, and vice versa. Plant managers coordinated daily through direct telephone lines, adjusting production in real time based on inventory levels and quality metrics. This industrial symbiosis was another wartime innovation that would become standard practice in the post-war chemical industry. Just-in-time inventory management and integrated supply chains all had roots in wartime exigencies that forced companies to cooperate and optimize like never before. Personnel management became increasingly sophisticated. Polymer faced constant labor challenges, finding trained workers, preventing turnover, maintaining morale during grueling work schedules. Women entered chemical production roles in unprecedented numbers, breaking traditional gender barriers. Many proved exceptionally skilled operators, often outperforming male colleagues in attention to detail and process consistency. Safety was a perpetual concern. Chemical plants are inherently dangerous environments. Toxic gases, flammable materials, high-pressure equipment, extreme temperatures, hazards lurked at every turn. Polymer implemented comprehensive safety training and rigid protocols. In August 1944, a reactor vessel ruptured, releasing a cloud of butadiene gas. Emergency response teams evacuated the area. Fortunately, no serious injuries occurred, but the incident prompted a complete safety review and additional protective measures. The explosion also attracted unwelcome attention. A blast that rattled windows miles away raised questions about what exactly was happening in Sarnia. Wartime secrecy prevented detailed public explanations. Polymer issued vague statements about an industrial incident while internally conducting exhaustive investigations to prevent recurrence. By late 1944, Polymer Corporation had established itself as a world-class synthetic rubber producer. The plant's efficiency surpassed many American facilities. Quality metrics met or exceeded U.S. government specifications for GRS rubber. This success attracted international attention. British officials visited Sarnia, impressed by what Canada had accomplished. American rubber company executives toured the facility, studying techniques they could adapt for their own plants. Rowzee, meanwhile, had become one of the world's foremost experts on synthetic rubber production. He was invited to speak at technical conferences, consulted on other synthetic rubber projects, and gained recognition as having achieved something many considered impossible. But perhaps the most meaningful validation came from the end users. Military logistics officers reported that vehicles equipped with Polymer's synthetic rubber tires were performing reliably in combat conditions. Truck tires were lasting thousands of miles. Aircraft installation showed excellent durability. Electrical insulation was holding up under demanding field conditions. The rubber worked. Soldiers' lives depended on it working. And it was working. By VE Day in May 1945, Polymer Corporation had produced over 100,000 tons of synthetic rubber. To put that in perspective, that volume was sufficient for approximately 50,000 military trucks, each requiring roughly 2 tons of rubber for tires, hoses, gaskets, and other components. 50,000 trucks that could move ammunition, food, medical supplies, and troops to wherever they were needed. 50,000 trucks that might not have existed if Sarnia's plant hadn't delivered. Behind the statistics and production figures were thousands of individual human stories. People who sacrificed, struggled, and persevered through conditions that tested them beyond normal limits. Ralph Rowzee aged visibly during those 3 years. Photographs from 1942 show a confident engineer in his mid-30s. By 1945, he looked a decade older. The stress of managing such a complex operation with impossible stakes had taken its toll. He worked 7 days a week, routinely pulling 18-hour shifts when problems arose, and problems arose constantly. His marriage strained under the pressure. Family life became nearly non-existent. Everything was subordinated to keeping production running. Dozens of other engineers and managers faced similar pressures. Vacations were postponed indefinitely. Hobbies were abandoned. Personal lives were put on hold for the duration. Plant operators worked rotating shifts that disrupted normal circadian rhythms. Night shift workers reported chronic fatigue. Health problems increased. Stress-related illnesses, exhaustion, industrial accidents. The toxic chemical exposures took a toll that wouldn't be fully understood for decades. Butadiene, styrene, and various processing chemicals that workers handled daily would later be identified as having serious long-term health effects. But in 1942, occupational health science was primitive. Workers were assured the exposures were safe. Many would pay the price decades later with elevated cancer rates and other chronic conditions. But in the moment, during the war, those risks seemed abstract compared to the immediate imperative of production. Women workers faced additional challenges. Cultural attitudes in the 1940s questioned whether women belonged in industrial settings, especially in demanding technical roles. Female engineers and chemists at Polymer had to prove themselves constantly, demonstrating competence that was automatically assumed for male colleagues. Sexual harassment was rampant and unaddressed. Women tolerated inappropriate comments and behavior because complaining risked termination. The few women in supervisory positions faced undermining from male subordinates who resented taking direction from a woman. Yet many women flourished despite these obstacles. Some of Polymer's best chemical analysts were women who brought meticulous attention to detail that caught problems male colleagues missed. Several women advanced to positions of significant responsibility, managing laboratory teams and overseeing quality control protocols. The broader community of Sarnia also sacrificed. The plant's operation created noise, odors, and pollution that affected residents for miles around. Chemical smells drifted over neighborhoods. Late-night operations disturbed sleep. Water quality in the Clare River degraded as industrial discharge increased. Complaints were met with patriotic appeals. This was wartime production. Discomfort was expected. Sacrifice was necessary. Citizens were encouraged to accept the disruptions as their contribution to defeating tyranny. Most did, but not without resentment. Homeowners near the plant saw property values decline. Commercial fishermen reported reduced catches. Children developed respiratory problems from chronic exposure to industrial emissions. These weren't hypothetical or exaggerated concerns. They were real impacts on real people, but addressing them would have required slowing production, and slowing production wasn't acceptable during wartime. After the war, veterans returned home with stories that provided context for these sacrifices. Truck drivers described surviving because their vehicles kept running when others broke down. Mechanics spoke about the difference quality rubber made in maintaining equipment under brutal conditions. Logistics officers recounted how reliable supply lines enabled advances that saved lives and shortened the war. Gradually, Sarnia residents came to understand that their discomfort, while real and significant, had contributed to something larger. The town's industrial output had materially affected the war's outcome. One particular story resonated. In 1946, a veteran named Douglas Martin visited Polymer Corporation. Martin had served as a supply sergeant with the Canadian 3rd Infantry Division during the Italian campaign and Northwest Europe operations. He'd coordinated truck convoys carrying essential supplies to forward positions. Martin stood at the plant gates and thanked every worker he encountered. He told them about trucks that rolled through mud, snow, and enemy fire because their tires, made in Sarnia from prairie grain alcohol, held together. He described soldiers who survived because supplies reached them when needed. "You weren't on the front lines," Martin told assembled plant workers at a special ceremony, "but you were absolutely part of the battle. Every ton of rubber you produced translated into missions completed and lives saved. Thank you doesn't seem adequate." Ralph Rowzee, attending that ceremony, reportedly had tears in his eyes. 3 years of crushing pressure, personal sacrifice, and constant uncertainty, all of it validated by hearing that the rubber had made a difference where it mattered most. What Polymer Corporation accomplished in Sarnia represented one of the most impressive industrial scale-ups in history. Taking a chemical process from laboratory concept to full production in 18 months, violated every conventional timeline for industrial development. The technical innovations developed during this crash program advanced the entire field of polymer chemistry. Rowzee's team pioneered process control techniques that became standard across the chemical industry. Their work on catalyst optimization influenced decades of subsequent research. One particularly clever innovation involved the emulsion polymerization recipe. Standard GR's formulations used a hot polymerization process running at about 50 degrees Celsius. Rowzee's chemists experimented with cold polymerization at around 5 degrees Celsius. Cold polymerization produced rubber with superior properties, better tensile strength, improved low-temperature flexibility, enhanced resistance to oxidation. The trade-off was significantly slower reaction rates, requiring larger reactors and longer batch times. By 1944, Polymer was operating both hot and cold polymerization processes, optimizing the choice based on the end-use application. Rubber destined for tire production might use cold polymerization for superior performance, while rubber for less demanding applications could use faster hot polymerization. This flexibility gave Polymer a competitive advantage. The plant could produce a wider range of rubber grades than competitors locked into a single process. Another breakthrough involved recycling and waste reduction. Early in production, substantial quantities of material were lost as waste during purification and processing steps. Chemical engineers systematically analyzed each waste stream, identifying opportunities for recovery. By redesigning separation processes and adding recovery equipment, Polymer dramatically improved yield. Material that would have been discarded was instead recovered and recycled back into production. This not only reduced costs but also eased pressure on raw material supplies. The environmental benefits, while not a primary consideration in 1942, were real. Less waste meant less pollution. Higher yields meant less resource extraction per unit of product. Polymer's success also demonstrated the viability of agricultural feedstocks for chemical production. Using grain alcohol to produce butadiene created a market for agricultural surplus while reducing dependence on petroleum. This bio-based chemical production was decades ahead of its time. In the 21st century, renewable feedstocks and bio-based materials would become major research areas. But Polymer Corporation was doing it operationally in 1943 out of wartime necessity. The knowledge generated at Sarnia spread throughout North America's rubber industry. Engineers trained at Polymer took those skills to other companies after the war. Technical papers describing process innovations were published in chemical engineering journals. Universities incorporated lessons learned into their curricula. German patent rights, seized from IG Farben after the war, were opened to public use. This democratization of synthetic rubber technology accelerated global development of polymer industries. Countries across Europe, Asia, and Latin America established synthetic rubber production using knowledge that Polymer and other wartime plants had pioneered. By 1950, synthetic rubber production exceeded natural rubber production globally for the first time. This shift fundamentally changed international trade, geopolitics, and economics. Natural rubber plantations, while still important, no longer held strategic choke point status. Developing nations lost leverage that Southeast Asian rubber dominance had provided. Meanwhile, countries with advanced chemical industries gained strategic advantage. The balance of power shifted subtly but significantly. Canada's role in catalyzing this transformation rarely receives acknowledgement. American rubber programs get most historical attention because of their larger scale. German developments are noted because of Nazi connections and wartime intrigue. But Canada's achievement, going from zero production capability to major supplier in 18 months, arguably represents the most impressive acceleration. Rowzee and his team had less time, fewer resources, and steeper learning curves than their American and British counterparts, yet they delivered results that matched or exceeded those larger programs. As 1945 progressed and Allied victory became inevitable, attention turned to the post-war future. What would happen to Polymer Corporation when military demand evaporated? Many wartime industrial facilities were expected to close, their missions completed. Synthetic rubber plants seemed likely candidates. With Southeast Asian plantations returning to production, natural rubber would flood back onto the market, presumably driving synthetic rubber into obsolescence. C.D. Howe thought otherwise. He recognized that synthetic rubber had advantages beyond wartime expediency. Performance characteristics for certain applications actually exceeded natural rubber. Cost structures, with proper economies of scale, could be competitive, and strategic independence from foreign rubber sources had obvious peacetime value. Howe decided Polymer Corporation would continue operating as a crown corporation. The government would own it, but the company would operate commercially, selling rubber on the open market in competition with natural rubber suppliers and other synthetic producers. This decision was controversial. Free market advocates argued government had no business running commercial enterprises. Why shouldn't Polymer be privatized, sold to private investors who would operate it for profit? Howe countered that national interest required maintaining domestic synthetic rubber capability. Selling to private owners risked having the facility shut down if short-term economics made natural rubber more attractive. Government ownership ensured long-term strategic resilience. Parliament debated the issue through late 1945 and into 1946. Ultimately, Howe prevailed. Polymer Corporation transitioned to peacetime operation as a government-owned commercial entity. The workforce adjusted to peacetime rhythms. Wartime's frantic urgency dissipated. Production schedules normalized. Safety improvements that had been deferred during the emergency were finally implemented. Ralph Rowzee, exhausted after 3 years of extreme pressure, considered leaving. He'd proven himself under fire. Opportunities beckoned at major American rubber companies willing to pay premium salaries for someone with his expertise. But Rowzee stayed, eventually becoming Polymer's president in 1957. He would lead the company for another 14 years, overseeing its evolution from wartime necessity into a profitable commercial enterprise. Under Rowzee's leadership, Polymer diversified beyond GRS rubber. The company developed specialized polymer products for industrial applications. Research labs investigated new polymer chemistries. Patents accumulated. By the 1960s, Polymer Corporation was not only profitable but was contributing to Canada's chemical industry development in ways that extended far beyond rubber. The technical expertise developed during the war years had become a platform for broader innovation. The plant's physical footprint expanded. Original buildings were supplemented by new facilities. Employment grew to over 2,500 workers by the late 1960s. Sarnia's Chemical Valley became one of Canada's premier industrial clusters, with Polymer as an anchor tenant. International recognition followed. Polymer won contracts to supply synthetic rubber to manufacturers worldwide. The Made in Canada label on rubber products became associated with quality and reliability. In 1971, the government sold Polymer Corporation to the Canada Development Corporation, a mixed ownership entity. Full privatization came in 1990, when Bayer AG of Germany purchased the company. The historical irony wasn't lost on observers. A plant built using German patents seized during wartime, established to break Allied dependence on Axis-controlled resources, eventually ended up owned by a German corporation. But that outcome reflected synthetic rubber's transformation from desperate wartime expedient into mature global industry. Polymer Corporation had helped catalyze that transformation. The Sarnia facility continues operating today, though under different ownership and with substantially updated technology. Modern synthetic rubber production barely resembles the wartime processes Rowzee's team pioneered. Computer controls replaced manual operation. Continuous flow systems supplanted batch processing. New polymer chemistry superseded simple GRs formulations. Yet, the fundamental achievement remains: taking an impossible challenge, working under extreme pressure with inadequate resources and knowledge, and delivering results that materially affected history's outcome. Ralph Rowzee retired from Polymer Corporation in 1971 after nearly 30 years with the company. He'd arrived in Sarnia as a 34-year-old engineer facing an impossible deadline. He departed as a 63-year-old industry statesman who'd built one of Canada's most successful industrial enterprises. His legacy extended beyond Polymer. Chemical engineers across North America had learned their craft from textbooks that incorporated techniques Rowzee's team developed. Thousands of plant operators had been trained using procedures his staff wrote. Entire industrial processes bore the imprint of wartime innovations created under his direction. Rowzee spent his retirement years quietly in Sarnia, rarely seeking publicity for his wartime accomplishments. When interviewed, he consistently deflected personal credit, emphasizing the team effort that made success possible. He passed away in 1994, at age 86. His obituaries noting his pioneering role in Canadian synthetic rubber production, but generally underplaying just how remarkable his achievements had been. J.R. Nicholson, Polymer's first general manager, went on to a distinguished career in business and public service. After leaving Polymer, he joined Brazilian Traction, later Braskem, eventually becoming that company's president. He was appointed to numerous corporate boards and became one of Canada's most respected business leaders, CD. Howe remained in government until 1957, earning recognition as one of the most influential Canadian political figures of the 20th century. His aggressive wartime industrial mobilization is credited with substantially accelerating Allied production and shortening the war. Critics accused him of authoritarian tendencies and excessive centralization of power. Supporters countered that extraordinary times required extraordinary measures. History's verdict has largely sided with Howe. Without ministers willing to cut through bureaucracy and force rapid industrial transformation, Allied production couldn't have matched Axis output soon enough to prevent even longer, bloodier conflict. Polymer Corporation, renamed Polysar in 1976, remained a Canadian success story for decades. The company expanded into petrochemicals, developing diverse product lines that extended far beyond rubber. Employment peaked at over 3,000 workers during the 1970s, making it one of Sarnia's largest employers. Privatization came gradually. Government ownership diluted through the 1970s and 1980s. The final transition to full private ownership occurred with Bayer's 1990 purchase. Today, the Sarnia facility operates as part of Lanxess, a specialty chemicals company spun off from Bayer in 2004. Modern production focuses on specialty synthetic rubbers for high-performance applications. The original GR17 production lines are long gone, replaced by sophisticated polymer synthesis processes that would astonish Rowzee's 1942 team. Polymer Corporation's wartime achievement influenced military logistics doctrine for subsequent decades. Never again would major powers allow themselves to become dependent on geographically concentrated sources of strategic materials. Diversification and domestic production capacity became central principles of defense planning. The U.S. maintained strategic material stockpiles partly in response to the military specifications require equipment to function with domestically producible materials wherever possible. Contingency plans for wartime industrial mobilization explicitly include rapid expansion of synthetic production capacity. Canada's confidence in its industrial capabilities was fundamentally boosted. A nation that had been predominantly agricultural and resource-attractive before World War II emerged from the conflict with world-class manufacturing and chemical industries. Polymer Corporation stood as proof that Canadian firms could compete globally in advanced technical fields. This confidence influenced post-war economic policy. Instead of remaining content with resource extraction and basic manufacturing, Canadian governments invested in science, engineering education, and industrial research. The National Research Council expanded. Universities strengthened engineering programs. Public-private partnerships modeled on wartime collaboration became standard practice. Sarnia's Chemical Valley emerged directly from Polymer's success. Once the synthetic rubber plant demonstrated that sophisticated chemical manufacturing could thrive in Sarnia, other companies followed. Petrochemical facilities, specialty chemical plants, and polymer producers established operations, creating an integrated industrial cluster. By the 1970s, Sarnia hosted one of North America's highest concentrations of chemical manufacturing capacity. This generated substantial employment and economic activity, though not without environmental costs that would become increasingly controversial in subsequent decades. The ethanol to butadiene chemistry that Polymer employed during the war experienced renewed interest in the 21st century. As petroleum prices rose and environmental concerns about fossil fuel dependence intensified, researchers revisited bio-based chemical pathways. Modern biotechnology companies investigated using agricultural feedstocks for chemical production, essentially rediscovering what Polymer did operationally in 1943. Several contemporary research programs specifically cite Polymer Corporation's wartime operation as proof that bio-based chemical production can work at industrial scale. The new idea of biorefineries converting plant materials into chemicals and polymers is in many ways a return to approaches proven viable 80 years ago. Climate change discussions occasionally reference synthetic rubber's carbon footprint. Natural rubber from trees is carbon neutral. The carbon released when rubber degrades equals the carbon absorbed during the tree's growth. Synthetic rubber from petroleum adds fossil carbon to the atmosphere. This oversimplifies a complex analysis. Natural rubber plantations often replace rainforest, destroying carbon sinks. Synthetic rubber production has become significantly more energy efficient since World War II. Life cycle analyses produce ambiguous results that depend heavily on assumptions and boundaries. But the fundamental question, should rubber come from trees or factories, traces directly back to the wartime decisions that established synthetic rubber as a viable alternative. Polymer Corporation was among the facilities that made that alternative real. What lessons does Polymer Corporation's story offer? First, seemingly impossible challenges can be overcome when urgency aligns with resources and political will. Rowzee's team accomplished in 18 months what normally required a decade, because failure wasn't acceptable and because C.D. Howe eliminated obstacles that would have delayed or blocked progress. Second, wartime innovation often produces peacetime benefits. The Crash program to develop synthetic rubber, advanced polymer chemistry, chemical engineering, and industrial process control in ways that benefited countless civilian applications. Necessity drove innovation that might have taken decades to emerge through normal research and development. Third, strategic vulnerabilities become obvious only in crisis. Before 1942, rubber dependency seemed acceptable because Southeast Asian plantations reliably supplied demand. It took Japanese conquest to expose how fragile that supply chain was. Modern societies face similar hidden vulnerabilities that remain unaddressed because no crisis has yet made them obvious. Fourth, individuals matter. Howe's decisiveness, Rowzee's technical excellence, Nicholson's administrative skill, these weren't interchangeable. Put different people in those roles, and outcomes might have been vastly different. We shouldn't over-romanticize the great man theory of history, but neither should we ignore how particular individuals' capabilities and decisions shape events. Finally, sacrifice has consequences. The workers who suffered health effects, the community that endured pollution, the families disrupted by wartime demands. They paid real costs for collective benefit. Acknowledging those costs doesn't diminish the achievement. It honors the full complexity of what success required. The next time you see a tire, consider the remarkable chain of events that made modern rubber possible. From prairie grain fields to chemical reactors, from desperate wartime improvisation to sophisticated modern industry, it's a story of human ingenuity under pressure. Thanks for watching. If you found this story compelling, hit like and subscribe for more untold stories from World War II. Which lesser-known WWII figure or event should I cover next? Let me know in the comments below. History isn't just about famous battles and leaders. Sometimes it's about engineers in Sarnia turning alcohol into rubber and quietly changing the world.